All right, we're back. We're on page 71 of the math analysis notes. We are in note 7. We are verifying trig identities. We're just talking about identities, really. So far, we've got the 8 fundamental identities. So these are things that are true, either by definition or because we've already verified them, and therefore we're allowed to use them to derive other things and verify other things. So let's see if we can write them down, because if you can't write them down, you can't use them, and if you can't remember them, you're gonna have a bad time. So let's see, reciprocal identities. So we got, which way do I like to write these? I'm gonna write cosecant x is 1 over the sine of x. I'm gonna say that secant of x is 1 over cosine. You could say them the other way. Honestly, you could say that sine times cosecant equals 1. Like, you could do whatever you want, really. They're only valid on the domain, right? But like, they have the same domain, so it's okay. And then cotan is 1 over tangent. All right, so those are our reciprocals. Those are by definition, basically. Ratio identities, these involve tangent and cotangent. So tangent is going to be sine over cosine. And then cotangent, because cotangent is the reciprocal of tangent, so we're just going to take the reciprocal of the identity that we just wrote, so, or the ratio, so cosine over sine. We use this when we were graphing tangent and cotangent. We use those identities. And the Pythagorean, so these are a really big deal, especially this first one. Sine squared plus cosine squared equals 1. So as long as x is the same, guaranteed to be true. And then the other ones, we've got tan squared plus 1 is equal to secant squared, because secant and tangent are secretly dating and they show up in the same place all the time together. And then 1 plus, whoa, how did I make a bunch of dots? Interesting. 1 plus, it threw me off my game because I was like, how did I do that? Cotan squared is equal to cosecant squared. So there you go. These are the fundamental identities. You will see them everywhere, and you can rearrange them. You could say tangent times cosine is equal to sine, I guess, if you wanted to. No one does that, really. But sine is 1 over cosecant, cosine is 1 over secant, cotangent is 1 over tangent. You will see that, or rather, tangent is 1 over cotangent. So you'll see these flipped over frequently. I mean, these, if you take the reciprocal of this, you actually just get this. And then these, this one comes from the unit circle. You definitely realize that one, whether you've been thinking about it or not. Like, that one's definitely true. This one comes up a fair amount in calculus in particular. And this one, it also comes up. It comes up much less. I tend to think of that one as annoying. I don't know. Don't let my bias be your bias. So let's take a look at a way in which we might use these, because the whole point of these gets really lost, because in like a pre-calculus setting, you get really obsessed with the manipulations and the ability to go from one thing to another thing. What you lose sight of is the fact that, like, when you're really doing these things in calculus, you don't have 2 expressions that you're trying to show are equivalent. You have 1 expression that you're trying to turn into another more useful expression. So for example, here, you're told that you want to graph this. Well, the way it's presently written, I don't see that happening. So if we look for commonalities, I see that I actually, it's a little buried, but there's a cosine of 3x and a cosine of 3x. So I'm going to factor that. So cosine of 3x. Now, after that, what's left? Cosine squared of 3x. So this only works because of the 3 x's. Sine squared of 3x. So that, you will find, is the best thing that can happen. The reason this is the best thing that can happen is that this cosine squared plus sine squared of the same thing, that's 1. So that whole thing there is actually just cosine of 3x. So much simpler. Now here, what are we going to do? Well, I don't know necessarily off the top of my head secant squared minus tan squared. I want to check and see what this equals. I suspect that it equals 1, but I'm not 100% sure. So what I'll do is, somewhere where I have space, I'll just write down what I have memorized. I memorized tan squared plus 1 equals secant squared. And it never hurts to check. So if I subtract tan squared from both sides, I would get 1 equals secant squared minus tan squared. So we got this. So let's see. I have this is the case. So when I go over here, I see secant squared minus tan squared of the same thing. So that's actually going to be 1. So I'm just going to say plus 1. And then this was a 1. So y equals cosine of 3x plus 1. And then you could graph it, right? So we went from this really weird thing to just getting cosine of 3x plus 1, which, you know, sinusoidal axis is 1. You can go up 1, down 1. The period's 2 pi divided by 3. The increment is that divided by 4, and then you're off, right? This is why trig identities matter. This is why you have to be able to deal with these things. It's to take an ugly thing, make it usable, right? Sometimes it's still not that great looking, but it's better. And it's really hard when you're first dealing with it to know what better means, right? But there's a rule because of the purpose of these. And that rule, and you're going to want to break it, but do not break it. When you are verifying identities, you must work on only one side. The reason you're working on only one side is you're telling yourself, the other side doesn't even exist, right? It's your goal. You're trying to get there, but it's not there. You can't like cross multiply. You can't add something to both sides. Like when you think of verifying identities, and you're going to lose track of it, I know, because everyone does. When you think of verifying identities, think back to the problem we just did. This cosine of 3x plus 1 wasn't there. Like we didn't know what it was. We had to like figure that out. That's what we're going to be doing. So I'm going to go through, in the next video, I'm going to start this. We're going to go through a bunch of techniques. There's not like one way to do these. There's a bunch. If you do a lot of them, like I've probably done thousands of them, you see the same things over and over. So I'm going to tell you the things that I saw over and over, and then send you on your way, and you're going to do a lot of them on your own, hopefully. And we'll see. So I'm going to end the video here, come back in the next one, and get started with that. So hope you find this helpful, and I will see you in the next one.